The Giant Magellan Telescope is something we've been working on for a long time, and we're making very good progress. We want to build this thing in Chile because it's the best place for astronomical observing. It has the clearest skies, the driest skies, most good weather. And we hope that we'll be able to use this thing both to look at the most distant galaxies in the universe and have some idea of where they came from and see those earliest formations. And also, closer to home, in our own Milky Way galaxy, we know that there are many stars around which there are planets orbiting. And a big telescope like the GMT will be very good at learning more about what those planets are and even searching for signs that there might be life on those planets. So from the beginning of the universe, tracing the matter all the way through to the formation of stars and planets and maybe even living things, the GMT is a tremendous tool for discovery. I've been working a lot on the discovery of the acceleration of the universe, this mysterious thing that the universe, which has gravity in it, we knew about that, which we thought would slow down the expansion over time, more if the universe was dense, less if the universe was of low density. We thought we would measure the density of the universe by looking at the history of cosmic expansion. But of course what we found is something completely surprising, which is that the expansion is speeding up over time. And we attribute this to the properties of dark energy. Now that's a good sounding name, but just because you have a name for something doesn't mean you really understand what it is. And so really, we're just at the beginning of trying to figure out what the dark energy is. And by observing distant objects, we've been using supernova explosions in the distant galaxies to measure their distances. By observing really distant things, you can trace out the history of the universe. The GMT will be very powerful for this sort of work and will allow us to study what was going on in the early phases where we don't really know if the supernovae back then are the same as the supernovae now, and where some of the uncertainties in our story for how the cosmic evolution has gone can be, some of those uncertainties can be reduced. We can really figure out better what the properties of the dark energy is, and to see whether it's the cosmological constant, which is a idea that Albert Einstein had, or whether it's some more subtle form of springiness about the vacuum itself. We're very good at learning how to detect the presence of invisible things. So for the presence of dark matter, which is stuff that has gravity that we can't see, we measure its effect. We see that it pulls on, say, stars or other galaxies, and we infer from that how much matter there is. For the dark energy, it's kind of the other way around. Could be just a quality of space itself or some kind of fluid that's in there that's transparent. But it has an effect. It makes the universe expand faster over time. So by measuring the relation between distance and velocity, tracing out the history of expansion, you can infer the presence of this dark energy and how it works. It's a little like looking out the window on a windy day. You look out the window on the windy day and you see a tree moving, and you say, well, why is the tree moving? And the answer is, of course, the wind. But you do not see the wind. What you see is the effect of the wind. And so in that way, the presence of the dark energy is something that we infer from the effects that it has. We don't actually see the stuff itself. There are things that astronomers really like. The joke is, why are astronomers on mountaintops? And the answer is because that's where people want to put them. The real point is that when you go to a mountaintop, you're above a lot of the atmosphere. You're also above a lot of the dust and other stuff that interferes with the light. In Chile, the fringe of the Atacama is a very good place for us because there are mountains, lots of mountains. You can pick the height you like. And we've chosen Las Campanas Peak, which is medium height place, so it's not that difficult to work. It is a place where the weather is very good, and when the conditions are as good as they get, they are the best in the world. There just isn't any place better. We also have had a lot of experience working in Chile. The Carnegie Observatories, who are hosts at the site, have been there since the 1970s, and so there's no surprise to us about the sort of complications of working at a great distance or in another culture. So we've had experience with that. It's worked out very, very well, and we're really looking forward to coming to Chile and building this fantastic thing for the world. A lot of the work that I've been doing has been building on work that people have done in Chile. So, for example, the business of using supernovae to measure the history of cosmic expansion had a very strong start in Chile at the Tololo supernova search, and the people following up that made a number of the very basic discoveries that made it possible to extend this to high redshift, to large distances, and see the change in cosmic expansion rate from long ago to now, and to see that the universe is speeding up. So people in Chile and work done in Chile has been very important. Also, our follow-up on the initial discoveries, or even the initial discoveries themselves, were done in large part at Cerro Tololo. We're using the telescopes in Chile. So this work, which led to the 2011 Nobel Prize in Physics, is something which has been really had a very strong set of roots in the country of Chile.